Okay, so as we look at these three examples down here, the first one that I hope you notice is that this example does not even fit in with this example type. We were talking about having two logs on both sides. So this one can certainly be worked. It just does not fit in with this example. This is the kind of problem that we had in a previous lesson. So on this one, hopefully you recognize what you do in that you only have a log on one side. So that means what you do is you take each side of this equation and it becomes the exponent to this as the new base. So this becomes 6 raised to the log base 6 of 3x plus 4 and 6 raised to the 1. So the original equation kind of becomes the exponents. And why do we do that? Because those two things simplify out, leaving us just the 3x plus 4 equal to whatever 6 raised to the first power is. Well, we know that's 6. Now this is just a regular algebra problem that we subtract 4. 3x is equal to, that's 2, divide by 3, and we get x is equal to 2/3. We do need to check and make sure that we don't get an extraneous solution, and we can usually tell we get an extraneous solution if when we plug this number in, does it cause this thing that's in parentheses to be negative? And I don't think it does. So we have log base 6 of 3 times 2/3 plus 4, and 3 times 2/3, that those two cancel out, so 2 plus 4 leaves me 6, so I end up with log base 6 of 6 is equal to 1, and that makes sense because 6 raised to the first power is equal to 6. So it's not an extraneous solution. B here does follow this. It is part of this example. I have a log on both sides. I just drop the logs and then I solve this problem as a simple algebra 1 problem. Subtract 3x from both sides and add 2 to both sides and divide by 4. And I get x is equal to 2. Plug 2 in right here. I get 14 minus 2, that's 12. That's okay. Plug in 2 right there. I get 6 plus 6, that equals 12. And that means that that one works. So I didn't have any extraneous solutions here. Part C right here may at first glance look like it's also not a part of this type, because we're supposed to be dealing with problems that have a log on both sides of the equation. Well, they're just being tricky here because you've got a log right here and you've got, and it's a natural log right here and a natural log right here. You've got nothing over here on this side. You've got a 0. So all you've got to do is move this log to the other side. Add the log of 4x minus 6 to both sides and you end up with natural log of 10 equal the natural log of 4x minus 6. And you may ask, well, why would we do that? Because we can. And if we can add that thing to both sides, and now I end up with a natural log on both sides, well, my natural logs can drop off. And now I can have a problem that's just a simple algebra problem. Add 6 to both sides, divide both sides by 4. And 16 divided by 4 is 4. You plug 4 in to the equation right here. 4 times 4 is 16. 16 minus 4 is 10. So it's not extraneous either. So could we take this problem right here and move it to this category over here where we have more than one log on one side? Absolutely. This problem could be worked this method or this method. Why would we prefer using this method? Because it's easier and it's shorter and it's faster. So if you can move one log to the other side and it doesn't have to combine with a whole number or anything like that, then you should. Because your logs, in order for them to drop off, they have to be the only other thing that's on each side of the equal sign. You can't have like a +1 on the end or a 2 out in front. It has to just be a log with an expression and then a matching log with another expression. That's all it can be in order to be worked in this method.